Good morning, guys. I know that this semester is going crazy. Frankly, it's the same thing for me. I don't know what we are doing right now, but I can tell you one thing. Yes, we're doing our best to come with really good solutions when it comes to class, lab, practice classes, SI classes. But I can tell you, and I mentioned this one right before we went for the spring break, that it takes a bit time to fix all those problems. So let's start with the lecture for now. And so when it comes to the lecture, I will post my slides. I will try to record video from my actual lecture, and I will put them on either Canvas, or I will put the link on Canvas and upload them on YouTube. You will see announcements on Canvas. So when it comes to the video, when it comes to the slide or lecture, I will try to do my best. Again, I'm not really perfect when it comes to editing videos or manipulating them, so please forgive me when it comes to the quality of the videos. But the lab for now, we are trying to come with online lab. The way we're going to do the lab, we will ask our TAs to do the experiments. They will use exactly same numbers that are written on the lab manual. So they will follow the lab manual, they will do the experiment, and they will share the result with you. Whatever they get, they will share it with you. And now we will ask you, do the pre-lab, do the lab, complete the calculations, and also complete the post-lab. And I'm gonna put quizzes on campus that they are related to pre-lab, lab, and the post-labs. When I say the quizzes, they are copy-paste questions from the pre-lab, lab, and the post-lab. You will see those on the Canvas. Please be patient until we upload them, and we will share that one with you, and I will make a bunch of announcements about them. For SI classes, I heard that they're going to do some some classes, and I will share the links or an announcement that I get from the LASO. For the practice classes, I'm talking with my my TAs to find the best way to help the class, and maybe we're gonna record, send some video that I'm making here. We're gonna do the same thing for the practice classes. I will record my TA. I'm talking about their practice classes, and I will share that one with you. Or maybe they can use the Elmo, go through the question, go through the worksheet that I post on Canvas, and we upload the file either on YouTube or on Canvas, and we will share the link with you. So please be patient until we get the all the details. So for now, I'm going to focus on this chapter. I will talk about the geometry, how to get the geometry of one system. Okay. At the beginning, I think, beginning of chapter 3, when I wanted to do the naming, I tried to classify the compound, and I said, the way we classify them, we need to know what type of bond we are dealing with. Is it ionic or covalent? If it's ionic, then the naming is going to be different. When it comes to the covalent, we said, hey, tell me how many from the first element I have, from second how many I have. Just simply say the numbers and name of the element, and same thing for the second one, like N2O5. Dinitrogen pentaoxide, 2 nitrogen, 5 oxygen. When it comes to covalent compound, you have a covalent bond. Okay, you have a covalent bond. Okay, what's the meaning of a covalent bond? We have two types of interaction. One, ionic. Ionic, you will transfer electron from metal to non-metal. So one, it will be cation with a positive charge, and non-metal, it will be anion with negative charge. Two particles with opposite charges are close to each other because of the electrostatic interaction. That's ionic interaction. Okay. Now the second one is covalent. Covalent, we do share 2 electrons per each bond. So 2 electrons for 1 bond. And we are sharing. We're not losing any of those electrons, because if we lose any of them, that's going to be ionic interaction. So I will be talking, this chapter, I will be talking about covalent interaction. Here, we need to know what's the meaning of polar bond and then electronegativity. Polar bond, any bond between 2 non-identical elements. If you have 2 non-identical elements and you make bond between them, when you make the bond, one of them it will have partial positive charge and the second partially negative. Okay. Negative. So like here, hydrogen, non-metal, fluorine, non-metal. We shared electron from hydrogen, 1 electron with another electron from fluorine. So we shared 2 electrons here. 2 electrons to make single bond. And as you see here, I put the arrow is pointing to fluorine, and this one here, it has a cross sign on it. That means it has partial, positive charge, and the fluorine got a bit electron, and it's not entire, electron, like we say the density of the electron, or a cloud of the electron, got closer to fluorine. So hydrogen lost something, but not the entire cloud. And because lost something, it will be positive. Why positive? Because we do have a proton. We did not lose the proton. This one, it will have negative charge. Why? Because we did not increase number of protons when we got some partial electron density. If you are sharing 2 electrons between 2 identical elements, a cloud here, it will have symmetry, so it's completely, kind of like, I can transfer, this half to the second one, or, I can chop it to 2 identical halves. When you share electrons between 2 non-identical elements, one of them will get some electron, and as you see here, this one got bigger, that one got smaller. Okay. Extreme case of any, any covalent bond, it will be ionic bond. In this case, it's sharing. It's not sharing anymore. It's not fair at all. This element, the one on the right, lost the electron, lost it to the left part. So this one now, it has extra electron. It will be anion, and that species, it will be cation. 2 particles are attached to each other because of the electrostatic interaction. Not sharing. Not sharing. And again, in this chapter, I'm going to focus on sharing. I don't have anything to do with the electrostatic interaction. Okay. What's electronegativity? Electronegativity, it will have meaning when you are talking about covalent bond. So you need to have like a bond that you got that bond through sharing, not transferring electron. Okay. Electronegativity is equal to the ability of pulling bonding electron to yourself. So we have one element attached to the second one, and somehow that element is stronger. It's stronger when it comes to bonding electron. Managed to pull the electron to itself. We said that element is electronegative. It has higher electronegativity. And the one that lost electron, we say, is electron positive. Electronegativity from left side of the periodic table, so from left side of the periodic table to the right side, it increases. Left to the right side, it increases. And down in one group here, if you take one group and you go down, decreases. Okay. So if you choose any group, let's say we go with fluorine, fluorine group 7 or 17. Fluorine has higher electronegativity than the chlorine higher than bromine, and bromine higher than iodine. So if you want a group, when you go down, electronegativity decreases. Well, if you take, for example, sodium, and you move to the right side. So from sodium, I go with magnesium, and then aluminum, silicon, phosphorus. From left to right side, electronegativity decreases. From up, down, decreases. So you need to know this one because it's really important when it comes to determining central atom. So from now, I want you to remember this one. You write this one for yourself. You say electronegativity to the right side decreases, down, decreases. So now compare electronegativity of carbon versus, let's say, nitrogen. Next one, we go, for example, with phosphorus, sulfur, and aluminum. This is from left to right side of the periodic table. Nitrogen is on the right side of carbon, so electronegativity of carbon is less than electronegativity of nitrogen. So we say carbon, it will be central atom. Okay, between these two, carbon, it will be central atom. And you attach any nitrogen, anything you have to carbon. How about this three? This is maybe not actually a good example. Let's replace this one by another element. I go with silicon. And in this case, we have phosphorus, sulfur, and silicon. So I will say silicon, it will have the lowest electronegativity. After that one, we go with sulfur, and then phosphorus. So electronegativity of silicon less than sulfur, and sulfur less than phosphorus. That means between these three elements, if you want to choose one central atom, it will be silicon, if you have to choose one. Well, for those two, we said carbon. Okay. Okay. So from left to right side of the periodic table, electronegativity increases, and from one group, from higher side of the or top of the group down, decreases. Fluorine has the highest, and francium, it has the lowest electronegativity. So we say this one is electronegative, francium electropositive. Okay. We want to practice. Okay. We want to practice octet rule, or we want to get the Lewis structures. Okay. First thing that you need to know, if you want to get Lewis structure of any compound, you need to know the meaning of octet rules. Octet means 8. Try to make any element, okay, try to increase number of valence electrons of any element to 8. If you have 8 electrons, that system will be really stable. Okay, really stable. And we go with this one. If we have any element from second period of the periodic table, carbon, nitrogen, oxygen, fluorine, make them 8. Give them enough electron until they reach 8 valence electrons. And I'm going to talk about the valence electrons, what I mean by valence electrons. If you have here, if you have elements that belong to the second or third group, you can't make the octet rules. Because remember, we're talking about octet, about covalent bond. Covalent bond, we get it through sharing the electrons. Okay. Boron has 3 valence electrons, because it's a group 3. If you share 3 electrons, you will get 3 extra. So it will be 6. Still, we are far from 8. We are far by 2. So we can't make the octet rule. However, B is a group 2. Beryllium is a group 2. Maximum valence electrons that you can, get this is 2, you share those two, it will be 4. Way far from 8. How about element that they have, they have d orbital? Okay, when I say d orbital, that means elements that they are belong to the third or more period of the periodic table. So any element from third level, n equal 3 or higher, they can violate the octet rules. It doesn't mean that if they follow is wrong. They can follow, that's completely fine. But if they violate the octet rules, again, that's acceptable because they can do it. Okay. Here, first thing that we need to do when it comes to Lewis structure, we need to know the valence electrons. We need to know how many valence electrons we have. The way you get the valence electrons, if you know the symbol of the element, if they give you the formula, just simply find that element inside the periodic table and see the group for it. If you know the group for it, then you got the valence electrons. And here, like I have H2O, hydrogen is the first group, so I'm going to say hydrogen is going to give me 2 valence electrons. Oxygen is a group 6, so I get 6 valence electrons from oxygen. So totally, I have 8 valence electrons. That's the way we get the valence electrons. If you have charge, you need to include that one in your calculation. Remember, positive charge, that means you are missing electrons. So if it has positive charge, you will subtract electron from the system. You will subtract electron from the total valence electrons. If the charge is negative, you will add the electron. Let's say this one was plus 1. Again, H2O plus 1. Then the total valence electrons will be 8 minus 1, it will be 7. If this one is minus 1, then the total will be 8 plus 1 equal to 9. Okay. So now I'm going to practice how to get Lewis structure of any element. Okay. So let's practice how to find Lewis structure of any compound. Okay. I go with CF4. CF. So first step, find valence electron. Okay. Valence electrons. Find the valence electrons. We go with, I have 1 carbon plus 4 fluorine plus charge. Okay. Plus charge. Charge for this compound is 0 because there is no charge here. So I'm going to say 1 multiply. Fluorine is a group 4. Carbon is a group 4. Fluorine is a group 7. So we go with 1 multiply. For carbon, we have 4 electrons plus fluorine, we have 4 of them multiplied. 7 for each fluorine plus charge is 0. So we get 32 electrons. 32 electrons. Now we need to write the electronegativity. Electronegativity to the right side decreases, down in one group decreases. So electronegativity of carbon is going to be less than electronegativity of fluorine. That means carbon is the central atom. So you start with this. Carbon is the central atom. You put 4 fluorines around carbon. Use 2 electrons to make 1 bond. We are going to share 2 electrons. So I use 1 electron from carbon, 1 from fluorine, share them to make a bond. And we call this bond sigma. First bond always going to be sigma. Okay. So I'm going to say totally I have 32 electrons. I will write it here, 32 electrons. Minus, I use 2 of them for 1 bond. I will make second bond, third, and here is the 4. So we made 4 bonds, and we use 2 electrons for each bond. So it will be plus 24 electrons. Okay. Now, we said we need to use the octet rule to make total valence electrons of each element equal 8. Draw a circle around this atom. You see 1 electron here, and it's gaining 1 through sharing, so totally it has only 2 electrons for now. 2 electrons. We want to reach 8. So I'm going to add 6 electrons to it to make it 8. So I will add here 6 electrons to make it 8. So I'm going to say minus 6 electrons for 1 fluorine. And I will do the same with the rest. So I use 6 electrons for each fluorine to make it up. We have 4 of them. So we are left with nothing. Now let's check the octet rules and see whether we managed to reach the octet rules or not. So you draw a circle. Again, you draw a circle around each atom. I see 7 electrons inside this circle. So I say 7 plus. And it's gaining 1 through a sigma bond. So you say plus 1, 8. Okay. 7 plus 1, 8. So we managed to make the fluorines octet. That's good. How about the carbon? You draw a circle around carbon. And I'm going to say here, for carbon, I say, I see 4 electrons inside the circle. And we made 4 sigma bonds. That means carbon is going to get 1 electron per each sigma bond. So you say 4. Also, carbon is going to be 8 or octet. 8 or octet. Something that I need to mention here. When I got the, when I built the sigma bond, I started with the fluorine to make it octet. Question is, why don't we start with carbon and then make the, the fluorine octet? You need to follow this box here. This one, it says electronegativity of carbon less than electronegativity of fluorine. That means if you do have extra electron, give it to fluorine first. And that's the reason that I started with the fluorine first. And when I made all fluorines are octet, then I look to carbon. Okay. We need to check the outer atom. If they are octet, now you can look to the central atom and check, see whether they are octet or not. If they are, that's good. Not, then try to make them octet. Okay. Next one, I'm going to talk about formal charge. Formal charge for any element. Okay. Any element is going to be equal to valence electrons of the element minus half of bonding electron plus non-bonding electrons. Okay. Bonding electrons, half of the bonding electron, bonding electrons and non-bonding electrons. Any of this pair, we call them non-bonding electrons because they are not connected to another L. They are attached to only one. Okay, only one. So we don't say we don't call them bonding electrons. Okay. How about those? those are bonding electrons. Why? Because you use them to make one bond, to attach two atoms to each other. Any of those, we call them bonding electrons. Okay. So I will practice this formula on this molecule and find the formal charge for any element. So structure is carbon, fluorine, you have 4 of them. And each fluorine, it has 6 non-bonding electrons. Okay. Let's find the formal charge. Formal charge, it says equal to valence electrons minus half of bonding electrons plus non-bonding. For example, formal charge of fluorine. I'm going to call this 1, 2, 3, 4. Formal charge of fluorine number 1 is equal to. Fluorine is a group 7. Fluorine is a group 7. So I say 7 valence electrons for fluorine. Minus number 1 is attached to carbon. We use 2 electrons to attach it to carbon. So we have 2 electrons for this sigma bond, so half of the bonding, half of 2 plus, and this fluorine we see 3 non-bondings. 1 pair, that's the second pair, and here is the third pair. So we have 6 non-bondings. So it will be 7 minus 1 plus 6 equal to 0. Formal charge, you write the top of any element. Here, formal charge, fluorine will be 0, 0, 0. You can practice it for number 2 to 4. You will get 0 for that. How about formal charge of carbon? Formal charge for carbon. Carbon is a group 4. So you say 4 valence electrons for carbon. Minus half of bonding. When it comes to carbon, we have 4 sigma bonds, and we are using 2 electrons for each sigma bond. So it will be half of 8. Plus, how about non-bonding? Do we have any lone pair? I call those lone pair. Do we have any non-bonding or lone pair electron on carbon? No. So it will be 4 minus 4, 0. You add the formal charges. When you add all the formal charges, they will be equal to charge of the compound. This is the compound. The compound does not have any charge. Charge is equal to 0. Charge is equal to 0. So when you add all the formal charges, they need to be equal to this number. Otherwise, you made a mistake. Somewhere you made a mistake. Okay. This is one way to find the formal charges. I'm going to show you another way to get the formal charge. Choose any element. Okay? Choose any element and draw a circle around that element. Let's say number 3. And say formal charge of fluorine number 3 equal to. Fluorine is a group 7. You say 7 minus, how many electrons do you see in this circle? I see 7 electrons. 1, 2, 3, here 5, 7. 0. So simply you say fluorine is a group 7 minus, I see 7 electrons inside this circle equal to 0. So you got the formal charge. How about carbon? Formal charge of carbon. Carbon is a group 4. So I say 4 minus. Draw a circle around carbon. I see 4 electrons inside this circle. 0. This is way easier than using this formula, so simply just draw a circle around that element and it will give you, the formal charge. Okay. Let's practice another one. And it's going to be example from your slides. It says H2O. Okay, H2O. So first step, find valence electrons. You go with 2 hydrogen plus 1 oxygen. Charge is 0. So it will be 2 multiplied 1 plus 1 multiplied 6. Why 6? Because oxygen is a group 6. Hydrogen is a group 1. And oxygen is group 6. Charge, this compound does not have charge, so it will be 0. We have 8 electrons. Okay. We have 2 elements, hydrogen and oxygen. Write this one. Never ever put hydrogen as a central atom. Hydrogen cannot be a central atom. Why hydrogen cannot be a central atom? Hydrogen has only 1 electron. Only 1 electron. So that means hydrogen cannot make 2 or more bonds. Hydrogen can make only 1 bond. Okay? Only 1 bond. So never ever put hydrogen as a central atom. So in this case, I don't care about the electronegativity, hydrogen cannot be a central atom. So I go with oxygen as a central atom. Put hydrogen. Here, hydrogen. Okay? And use 2 electrons for each one. So I'm going to use 2 electrons for each one. This one is sigma. So I have 8 electrons minus 2 electrons. I made 2 bonds, so I'm plus 4. Now, when it comes to the extra electron, we said draw a circle around outer atom and see whether they are octet or not. Hydrogen cannot make the octet group, or cannot make the octet group. Why? Because it has only 1 electron. You share it, you get 2 electrons, way far from 8. Hydrogen, it will be 2. And for hydrogen, this is okay. Only hydrogen. Hydrogen, it can make only 2. How about that one? 1. I see 1 electron here, gets 1 through sigma, 2. So hydrogen is fine. But I'm plus 4 electrons. So I need to do something with these 4 electrons. If you are done with outer atoms, now you can give them to the central. So I have 4, and I give them to the central atom. Draw a circle around this atom and check the octet group. Okay. I see here, I see 6 electrons, so I'm going to say 6 electrons, and we made 2 sigma bonds, so we get 2 electrons here. It will be 8. So we managed to make the octet group. Okay. How about the formal charges? Formal charges, the way you do it. Okay. Say hydrogen group 1 minus. How many electrons do you see in this circle? Only 1. So that one is 0. Okay. Formal charge of hydrogen. How about oxygen? Oxygen, formal charge of oxygen. You go with oxygen is a group 6, so you say 6 minus. I see 6 electrons inside this circle, 0. So we have 2 hydrogens, and each hydrogen it has 0 formal charge. So we have 2 zeros. And how about oxygen? Oxygen also is 0. The total charge is going to be equal to 0. And H2O does not have a charge. Charge is equal to 0. So I got it correct. replace hydrogen by another element, like say fluorine, and get the get the Lewis structure for it. So then you can understand the role of hydrogen. We did the H2O. Now let's change it to F2O and get the Lewis structure for it. So I have F2O. It will be 2 fluorine plus 1 oxygen plus the charge. Charge is 0. So it will be fluorine is a group 7. This one is a group 6. So you go with 2 multiplied 7 plus 1 multiplied 6. You have 20 valence electrons. Electronegativity of fluorine higher than electronegativity of oxygen. So oxygen is going to be the central atom. Here is oxygen. Okay. And I put 2 fluorines. I use 2 electrons for each bond. So I have 20 electrons. I use 2 electrons for each bond. I made 2 sigma bonds. So it will be plus 16. Okay. Now I go to this one and I use the electronegativity rule. Electronegativity rule says a fluorine higher than oxygen. So if you do have extra electron, give it to the outer atom. Outer atom, this one, it has only 1 and it's gaining 1 through sigma bond, so it will be 2. Give it 6 to make it octet. So I'm going to give fluorine 6 electrons, make it octet. So minus 6. And I will give this one also 6 electrons. So minus another 6. So it will be plus 4 electrons. I made each of this fluorine octet, but still I do have extra electrons. I'm going to give them to the central atom. Check the rules. Fluorine. I see 7 electrons. I say 7. And each one is making 1 sigma bond, so it's going to get 1. So this one is 8. 7 plus 1, 8. How about oxygen? Oxygen. I see 6 electrons plus 2 through 2 sigma bonds, 8. So all my elements are octet. Let's define let's calculate the formal charges. Formal charges. Formal charge for any of these elements. You start with here, formal charge going to be equal to. I said choose the element. This is a fluorine. Fluorine is a group 7, so you say 7. Minus, look at the number of electrons that you see in this circle. I see 2, 4, 6, 7. 0. Again, here is a group 7 minus 7 electrons. We see 7, 6 here, plus 1, 0. Oxygen. Oxygen is a group 6 minus, I see 6 electrons here, 0. When you add all the formal charges, they will be equal to 0. And this compound does not have any charge. Okay? I said, I want to do the F2O example because I want to show you the role of hydrogen here. We had extra electrons. We had 16. We gave them to fluorine first. We gave each fluorine 6 to make each fluorine octet, and then we gave it to the oxygen. Compared with the previous example, we used 4 electrons. We ended with 4 extra. I said, do not give extra electron to the hydrogen. Why? Because hydrogen can accept only 1. So hydrogen will be 2. and hydrogen is down. So if you have extra, give it to the central atom. And that's the reason I did not draw any any dot around hydrogen. Let's make this example a bit complicated. And then I go with CO2 example, and I want to show you how to get loose the structures of CO2. You go with valence elements. We have 1 carbon plus 2 oxygen, charge is 0. So 1 multiplied carbon is equal 4, plus 2 oxygen is equal to 6, and charge is 0. You are dealing with 16 electrons. Electronegativity of carbon less than electronegativity of oxygen. That means carbon is the central atom. Okay, carbon is the central atom. So here I have carbon, and I have 2 oxygen, 2 oxygen. Use 2 electrons per each bond. 2 electrons per each bond. We made 2 bonds, so it will be 16 minus 2 per each bond, and we made 2 of them, so it will be plus 12. Use the electronegativity rules. Give the extra electron to outer atoms first. If you have extra, after that, then you give it to carbon. I have 12, I give each outer atom 6 to make it octave, so minus 6. Another 6, 0. Draw a circle around each atom to see whether you met the octave rules or not. Here, oxygen, I see 7 electrons. Plus we made 1 sigma, so it will be 8. Oxygen octave. This one also, I see 7 electrons plus 1 through sigma, 8. But carbon, see 2 electrons, we made 2 sigma bonds, 4. Carbon is not octave. Remember, we said if we have elements from second period of the periodic table, you need to make them octave. So I need to make carbon octave. Somehow I need to get electrons from somewhere to have 8 of them here. And run carbon. You have a couple of options. You can share 2 lone pairs with carbon. Carbon has only 4. It's missing 4 to be 8. So we can share 4 from oxygen with carbon, and it will be octave. Or you can share 2 from this carbon oxygen, 2 from another oxygen, and then this one will be octave. So first option, I will use this one as a reference. So first thing that I'm going to do, I'm going to say, let's keep this one as a reference and manipulate this structure to make carbon octave. I will share 1 lone pair from oxygen number 1 and 1 from number 2. So let's share 1 lone pair from each oxygen. Each oxygen attached to carbon by 1 sigma bond. In each oxygen it has 3 lone pairs. Okay. I will use this lone pair, I will use it to make a bond between these 2 elements. So I'm going to erase it and I will put it here. And then I will do the same thing with this lone pair, share it with carbon and make double bond. Okay. Double bond here, the second bond, we call it pi bond. Okay. This is one way to make carbon octet. Draw a circle, run carbon, carbon. I see 4. We made 4 bonds. There's 8. How about oxygen? Oxygen, this one. I see 6. Made 2 bonds. 8. Same story for that one. 6 plus 2, 8. So this is the first Lewis factor. How about another? I said you can share 2 lone pairs from number 1. 2 lone pair with carbon, and then carbon will be octet. So I'm going to do this one. I'm going to use this one as a reference. I will erase 2 of this lone pair and make double and triple bond. So I go with here. I have carbon, oxygen number 2. It has 3 lone pairs. Keep this one as it is. Oxygen number 1. It has 3 lone pairs. I'm gonna, ignore this one. I'm gonna use 2 of these lone pairs to make double and triple bond. So here, double and triple bond. So I will have only one lone pair, only one lone pair around oxygen. Okay. Draw a circle around each atom and see whether you met the octet rules or not. This oxygen, I see 5 electrons. We made 3 bonds. It will be 8 carbon. I see 4 electrons. We made 4 bonds. 8. This oxygen. See 6 plus, 7, my bad. 7 plus 1 will be 8. This is sigma, that one sigma. First bond always sigma, second and third, they will be pi. Okay. So I shared 2 lone pairs from the oxygen number 1. You can go with 2 lone pairs from oxygen number 2 instead of 1. Okay. So I keep 1 as it is. I keep this one as it is. It has 3 lone pairs attached to carbon. The carbon is attached to oxygen number 2. Erase 2 of the lone pairs and make double and triple bond. So I will here made triple bond. I use 2 of the lone pairs. I have only 1 left. And now if you check the octet rules, this one, I see 7 electrons plus 1, 8, carbon here, 4 plus 4 bonds, 8, oxygen, I see 5 plus 3, 8. So we made all of them octet. Now the question is, which one of this structure, which one of this Lewis structure is the best? Okay. We need to talk about, energy of Lewis structures. So I'm going to switch to my PowerPoint, and I'm going to show you how to assign, or order of these Lewis structures based on formal charges. So now, what I want to do, I want to order the 3 Lewis structures that I got based on energy. But I will use the formal charges to order them. And I'm going to tell you or show you how to get that one. So the valence electron, with a formal charge, we say the valence electrons minus non-bonding electrons plus half of bonding electrons. Rule. When you add the total, the formal charges, they need to be equal to the charge of the compound, or molecule, or ion, or cation. Next one. If you have more than one Lewis structure, the one with the lowest formal charges is the best, okay? You have more than one Lewis structure, the one that it has the lowest formal charge is the best. So if you have one that it has all of them 0, 0 for formal charges, and you have one that it has 0, 0, plus 1, minus 1. Okay. I will say the first one is going to be the best. Why? Because all the charges are zeros. If you have to, okay, if you have to go with the charge, okay, and by chance the charge this time is negative. A negative charge has to be on the most electronegative element. Let's say we have carbon and oxygen. And one of them, it will have a negative charge. Now I can have a negative charge on on carbon or a second element. I will say carbon in this case, it has the lowest electronegativity. So carbon is not going to have that negative charge. Negative charge is going to be either on oxygen or nitrogen. Okay. And I'm going to use this slide to order Lewis structures that I got for carbon dioxide. So we have 3 Lewis structures. We need to find the formal charges for them. So let's get the formal charges for each. Formal charge of this element, we say this is oxygen, group 6, minus. I see 6 electrons, so it will be 0. How about carbon? Carbon is a group 4. So you say 4, minus. I see 4 electrons here. So this one also it will be 0. Oxygen, 6 minus 6 electrons here, 0. So I got all of them 0, 0, 0. Next, oxygen here. Oxygen is group 6, minus. I see only 5 electrons. So it will be plus 1. Carbon, group 4, minus. I see 4 electrons inside circle, 0. This oxygen. It's a group 6, minus. This time I see 6 and 1 here, 7. It will be minus 1. When you add them, plus 1 to 0 is going to be plus 1, minus 1, 0. And that's the charge of CO2. Here, formal charge, it will be 6 minus 7, minus 1. This one it will be 4 minus 4, 0. That one it will be 6 minus 5, plus 1. So now try to use formal charges to order these Lewis structures. Okay. And let's call this one E1, E2, and E3. We want to order them based on their energies. I'm going to say the one that it has the lowest formal charges, it will be the most stable structure. Okay. We have 0, 0, 0. So number 1 is the lowest. Next, compare 2 and 3. 2 and 3. This time you do have charges. If you compare them with the first one, 0 plus 1, 0, 0. This one is 0 minus 1. So this structure is going to be higher in energy than the first one. Okay. Number 2, number 3. We have 0 for carbon in both cases. That's good. When it comes to oxygen number 1, we have it plus 1, minus 1. Minus 1, plus 1. So they are the same. Okay. Well, only thing we did, we changed position of the charging. Okay, I'm going to say energy of the second structure is going to be equal to the third one. You cannot say which one is more stable. Only thing we can say, number one is more stable. Because number one is the most stable structure. That means if you really use a device to look at CO2 molecule, you will see that the length of this bond is going to be close to a double bond. Okay, close to a double bond. And same story here. We've got three structures for CO2. We call this structure, we call them resonance structures. Okay. And usually the way we show the resonance structures, we put this symbol between them. That means this one can be converted to that one. So I can put here arrow between them. That means the first one can be transferred to the second, and the second to the third one. Okay. Let's put it here, for example. Okay. Any one is possible, but the first one is the most stable low structure. Okay. So till now, I showed you how to get the light. I showed you how to get loose structure of any compound. Also, we practiced the formal charges and the octet rules, and at the end, we order the structures based on their energies. But I did not practice a structure with a with a negative or positive charge. I mean, like, I did not practice any anion or cation. Let's do one more, and then you'll know how to use the charges when it comes to anion or cation. In your slide, you have this one. You have 9 that it says NCO minus 1. NCO minus 1. Okay. And they say find the resonance structure for this anion. I see 1 nitrogen plus 1 carbon plus 1 oxygen and plus charge. Nitrogen is group 5. This one is a group 4. And oxygen is a group 6. And the charge is negative. Because it's negative, you will add 1 electron. Because it says minus 1. If it's plus 1, then you will subtract. So I go with valence electrons. The total valence electrons, 1 multiplied 5 for nitrogen, plus 1 multiplied 4 for carbon, plus 1 multiplied 6 for oxygen, plus 1 here for the negative charge. So total we have 16 electrons. Electronegativity of carbon is less than electronegativity of nitrogen, and nitrogen is less than oxygen. That means carbon is a central atom. So you put carbon as a central atom. And distribute the rest of the elements around carbon. So I will put, say, nitrogen, for example, here, and oxygen is there. And I'm going to use these 16 electrons to make all these elements octet. So I go with 2 electrons per each bond. And this is sigma bond. So I need 2 sigma bonds, and then I use 2 electrons for each bond. So we are plus 12 electrons. Electronegativeness says oxygen is the highest. If you have extra electron, give it to oxygen. So I go with oxygen first. I give oxygen 6 minus 6. Then I go with next element, it's nitrogen. I give nitrogen 6, 0. Carbon is not octet. We need to fix it. Rest are octet, they are okay. Oxygen 7 plus 1 through sigma bond 8. Here again 7 plus 1, 8. Carbon 2 plus 2, 4. You need to fix it. We will do same stuff like CO2. We can share 2 lone pairs from nitrogen with carbon, or 2 from oxygen, or 1 from each. Or 1 from each. So I will use this one again as a reference, and I will try to make carbon octet. So first assumption, share lone pair from each element. We have nitrogen, carbon, oxygen. There's a sigma bond between each two. Here, there's a sigma bond between nitrogen, carbon, and oxygen. Okay. I'm going to share one lone pair with double bond. So from nitrogen, I use one lone pair, 2 there. And from oxygen, I'm going to share 1. So I use this. I have 2 lone pairs. Check the octet groups. This one, we see 6 electrons plus 2 for 2 bonds, 8. Carbon 4 plus 4 bonds, 8. Oxygen 6 plus 2, 8. How about the formal charges? Formal charges, nitrogen is a group 5 minus, I see 6 electrons, so it will be minus 1. Oxygen is a group 6, I see 6 electrons inside circle, 0. Carbon is a group 4 minus, I see 4 electrons, 0. Next, Lewis structure. Instead of sharing one lone pair from each element, share 2 lone pairs from either nitrogen or oxygen. I go with nitrogen first, so I share 2 lone pairs with carbon, and I keep oxygen as it is. Use this one as a reference. You will use 2 of the lone pairs. So I use 2 of them, only 1 left. Now check the octet group. This one is 5 plus 3, 8. 4 plus 4, 8. This one is 7 plus 1, 8. Formal charges, nitrogen, group 5 minus 5, 0. Carbon, 4 minus 4, 0. Oxygen is a group 6. I see 7 electrons, minus 1. Another possible Lewis structure, share 2 lone pairs from oxygen into that nitrogen. And keep nitrogen as it is. So I keep nitrogen as it is. And share these 2 lone pairs. Use 2 of them, only 1 left. Here, 1 left. Now check the octet group. This one is 6 plus 1, sorry, 7 plus 1. 7 plus 1, 8. 4 plus 4, 8. That one, 5 plus 3, 8. How about the formal charges? Formal charge, nitrogen is equal to 5. I see 7 electrons is minus 2. Carbon, 4. I see 4 electrons, 0. Carbon is equal to 4, so that's the reason I started with 4. Minus 4. How about oxygen? Oxygen in group 6, minus, I see 5 electrons. Okay. Plus 1. So now we need to order these loose structures based on their energies. Let's call this one 1, 1, 2, and here 3. Rule says the one with the lowest formal charges is the best. The one with the lowest formal charges is the best. So in this case, I'm going to look for really small numbers. First one, we have minus 1, 0, and 0. So that one, it can be an option. Second one, we have 0, 0, minus 1. Third one, it says minus 2 and plus 1. This one cannot be, so this one it will be structured with the highest energy. Ignore this one for now, because we have minus 2 and plus 1. We have two numbers that they are bigger than 0. But those two, at least they have two numbers that they are 0. 2 zeros here and 2 zeros here. Now, you need to look to the electronegativity. Electronegativity was saying that electronegativity of carbon less than electronegativity of nitrogen, and nitrogen less than electronegativity of oxygen. That means if there is a negative charge must be on the most electronegative element. Okay. If there is negative charge, it must be on the most electronegative element, which is oxygen. Compare 1 and 2. The negative charge is sitting on nitrogen in 1. And the second loose structure, the negative charge is sitting on oxygen. So between 1 and 2, 2 will be the best structure because the negative charge is sitting on oxygen. So I'm going to say E2 is the best. After E2, we'll have E1. And E1 is less than in energy. E1 is less than in energy than E3. Because E1, it has two of them are 0. While E3, it has two numbers that they are bigger than 0. Or at least they are not 0. Okay, so that's the way we find the order of energies for loose structures. So we said E2 is the best, and then E1, and after that one, E3. So here we have all loose structures of NCO, -1 and 9. So said, first one we call it sigma. So we have two sigmas, and here we have pi bonds. Okay. I will show you another example for resonance structures, and it's going to be CO3 -2. You have 1 carbon plus 3 oxygen, and the charge says -2. So I will add 2 electrons. So it will be 1 multiplied 4 for carbon, plus 3 multiplied 2 for oxygen, and plus 2 there. So totally we have 12 electrons. Electronegativity of oxygen higher than electronegativity of of 1 carbon plus 3 oxygen plus 4. Oh, my bad, sorry, my bad. This one is 3 multiplied 2. Sorry, this one is 6. And we have 3 here, so sorry about this one. 1 multiplied 4 plus here 22, 24. So we have 24 electrons. 24 electrons. So we said electronegativity of oxygen higher than electronegativity of carbon. So carbon will be central atom. Here's carbon. Put 3 oxygen around it. You have to use 6 electrons to make 3 sigma bonds. So minus 6 will be here 18. I'm going to give each electron 6 extra electrons to make it active. Minus 18 will be 0. But carbon is not active. You draw a circle around carbon. Carbon is a 3 plus 3, 8. So 6. Carbon is not active, while oxygen 7 plus 1, 8. I'm going to share electrons from each oxygen to make carbon active. And I go with this. We start with 1. So we get carbon. Carbon attached to oxygen number 1. We share 1 lone pair. If you share 1 lone pair, you will have only 2 on oxygen. The rest, keep them as they are. Or you can use lone pair from oxygen number 2. Or you can go with number 3. So I got 3 Lewis structures. 3 Lewis structures, and the only thing I did, I kind of like rotate double bond, or position of the double bond. Okay? And I put this sign between them to show you that they are resonance structures. That means this bond, 1/3 of the time is a double bond. 1/3 of the time. So this bond, at least, is going to be shorter than a single bond, because 1/3 of the time is double bond. Double bond is shorter than a single bond. And then it will move here. The second third of time, number 2 is a single bond, a double bond. And then you move it to number 3. Sorry, this one was 1, and here is a 3. You move the position of the double bond between carbon and oxygen number 3. So now, this one, it will be a double bond. Okay. Which one is the most stable Lewis structure? In this case, you can say all of them carry the same amount of energy. So we're going to say E1 equal to E2 equal to E3. So that means if you look to this anion and measure the bond length of any oxygen with carbon, it's going to be shorter of single bond, shorter of a single bond, but longer than a double bond. Shorter than single bond. Why? Because 1/3 of the time is a double bond, but it's not really a double bond because 2/3 of the time is a single. Okay, so only 1/3 is double bond. We name this bond here, we name this one is sigma. So we have 3 sigma bonds and 1 pi. Okay. So I'm going to say I have 3 sigma bond, and I have 1 pi bond. Okay. 3 sigma bonds and 1 pi bond. How about lone pair on the central atom? We do not have any lone pair on the central atom. Okay. I will use number of sigma, and also lone pair in the central atom to determine electron and molecular geometry of any compound, which I'm going to show you in my slides. Okay. Practice this too. We have carbonate, CO3 minus 2. When you get the formal charges, 1 oxygen to be 0, carbon is 0. We have -1, -1, so the total charge is going to be -2. We have 3 sigma bonds, pi bond, only 1 bond. And how about lone pair on the central atom? Nothing. Okay, so I'm going to say I have 3 bonding pairs, or 3 sigma, and lone pair on the central atom. Lone pair on the central atom equal to 0. I don't care about how many pi bonds we have. Okay? I don't care about how many pi bonds we have. And I will tell you why. So 3 sigma plus 0 lone pair on the central atom equal to 3. And this number is going to tell me what's the electron geometry of the compound, or which electron geometry I should expect to see. So from now, we will count number of sigma bonds and lone pair on the central atom. I don't care about the lone pair of oxygen because they are outer atoms, only the central atom. So from now, I'm going to switch to electron and molecular geometry, and I'm going to show you how to determine both of them. Okay. This theory, valence shell electron pair repulsion theory, says try to distribute the electrons in a way that you have the longest distance between them, or the biggest bond angle between them. Because each electron comes with negative charge. If you put it close to another electron, it will repel it. Okay. Now, if you have 4 of them, try to put them way far from each other in a way that you have the maximum bond angle between them. Okay. And I go with this one. Imagine you have only 2 pairs. Okay. 2 pairs. So I have 1 pair here, and let's say this is the second pair. Maximum bond angle that I can put between them, it will be 180. Okay, 180, they will be way far from each other. That's the best Lewis structure. Okay. Why? Because this bond, it comes with 2 electrons. That one with 2 electrons. They will hate each other because they are electrons. They will repel each other. You want to make the system stable, put them 180 degrees far from each other. If you have 3 pairs, then maximum bond angle that you can have, okay, maximum bond angle that you can have between this element, the central atom, and that one is going to be 120. Okay, that's the biggest one. Okay. So in this theory, we will try to distribute the electrons in a way that we have the biggest bond angle, because the system, it will be really stable. Okay. We will have 2 types of geometries. One, electron geometry. Electron geometry is going to be based on arrangement of electrons. You have the central atom, you assign the electrons around the central atom. Arrangement of electrons around the central atom will determine geometry of the compound. It's like, you know what, the central atom is going to be, it will be said, I put, stuff on the table. Whatever I put on the table, you will eat, okay? Because it's my house, my rules. That's going to be the rule when it comes to the electron geometry. So the central atom is going to tell you what's the, geometry. when it comes to the molecular geometry, really the geometry that we will be dealing with, in that case, we're going to say, we know what theoretically, what we should expect. Now, next thing is, how many outer atoms do I have? Okay. I need to ask myself. Fine. I go back, for example, here. I see 3 pairs of electrons. 3 pairs of electrons. Based on this one here, based on the valence shell, electron pair repulsion, if you have 3 pairs of electrons, the electron geometry that you can expect, sorry about that, electron geometry that you can expect, it will be trigonal planar. Trigonal planar, 120 degrees between them. Okay. The electron geometry is going to tell you, you have 3 pairs of electrons. Do you have 3 outer atoms? If the answer is yes, then you're dealing with a trigonal planar geometry. So this one, it will follow number of outer atoms around the central atom. And I will follow this slide. Okay. So whatever you do, please remember this slide. Okay. You go with electron number of sigma bonds plus lone pair. If number of sigma bonds plus lone pair equal to 2, the electron geometry is going to be linear. If it's equal to 3, we call it a trigonal planar. If the answer is equal to 4, it will be tetrahedral geometry. And if you got this one equal to 5, it will be trigonal bipyramidal. And if it's equal to 6, we say octahedral. We can have more than 6. We can have more than 6 sigma lone pair, but we're not going to go through those. Usually they cover them in organic chemistry and it's higher than the scope of this class. So please remember this slide. Okay. Sigma plus lone pair on the central atom. Okay. We don't care about outer atoms. And we go with this. Okay. We have AB2, so our atom is beryllium and chlorine. We have 2 chlorines. So total valence electrons, I will have 2 plus 2 multiplied 7, 14 electrons. I'm going to show you how to get the Lewis structure for this one and what's the electron geometry and the molecular geometry of this compound. So the compound, it says BeCl2. Valence electrons, you go with 1 B beryllium plus 2 chlorine. So it will be 1 multiplied 2 plus 2 multiplied 7. You have 16 electrons. Electronegativity of chlorine higher than the beryllium. So Be is the central atom. And Be is a group 2. Because it's a group 2, it's not going to make the octet group. Okay. So you go with B, attach it to 1 chlorine. And use 2 electrons to make sigma bonds. So here, 2 electrons per each sigma bond. I had 16. I use 2 for each one. Plus 12. And I follow this one and I give each chlorine 6 electrons to make them octet. You draw a circle around each element. I see here 7 electrons plus 1 So 1 sigma will be 8. Here I see 2 plus 2 sigma. 4. This one 7 plus 1 sigma. 8. So we met the octet rule for chlorines, but beryllium is not octet. And I told you, because it's a group 2, it can't make the octet rule. Okay. How about the 4 mole charges? 4 mole charge, this one, group 7, minus, I say 7 electrons. It will be 0. Here, 7 minus 7, 0. That one is 2 minus 2 will be 0. Somebody maybe ask or say that why don't you share lone pair from the from outer atoms with central atom and make it octet? We can give it a try. Let's go with here B. We're going to share 2 lone pairs. One lone pair from each chlorine or 2 lone pairs from one chlorine. So I go with 1 lone pair from each chlorine. If you share 1 lone pair from this chlorine, you will have 2 lone pairs there. So now you have 6 plus 2. We made 2 bonds. 8 central atom. 4, we made 4 bonds. 8 chlorine. 6 plus 2 bonds. 8. So we met the octet groups. That's a good news, but find the 4 mole charges. When you find the 4 mole charges for chlorine, it's a group 7 minus. I see 6 electrons here. 6 electrons inside circle is plus 1. And you do it for this one, you will get the same answer, 7 minus 6 plus 1. But for the central atom is a group 2 minus. I see 4 electrons inside the circle. So it's minus 2. Look to the electronegativity rules. Electronegativity of chlorine is higher than the beryllium. So if the electronegativity of chlorine is higher, and you do have negative charge, the negative charge must be on the chlorine. Must be. Okay, the negative charge must be on the chlorine. We have a positive charge, not even a negative charge, a positive charge on chlorine, which is really bad news. But we get the negative charge on the most electropositive element. So you give the negative charge to beryllium instead of chlorine, which is not a good one. And because the negative charge is sitting on the electropositive element instead of electronegative element, this is not a good structure. Okay. This is really bad one. And that's the reason we don't care about this one. Okay. So now let's talk about first structure. So the first structure, we have beryllium attached to chlorines. You need to write this one. Number of sigmas in lone pair in the central atom. So you say sigma for central atom. We have 2 sigma. Lone pair on the central. We call this pair of electrons, we call them lone pair. Okay. Lone pair for central atom, 0. Sigma plus lone pair equals 2. Okay. If sigma plus lone pair equal to 2, we say electron. Geometry it will be linear. And how about the molecular geometry? That one also it will be linear. That means the bond angle between them will be 180 degrees. 180 degrees. I'm gonna here write note. If lone pair on the central atom is equal to 0. If this one is equal to 0, then electron geometry will be equal to the molecular geometry. This one is the molecular geometry. The first one, we call it electron geometry. So use this one to predict the molecular geometry. If you do not have any idea about the molecular geometry, but you got the electron geometry, and by chance number of lone pairs on the central atom is equal to 0, so use the same name for both. So in this case, I'm going to say electron geometry, it will be equal to molecular geometry, and both they will be linear. So we practice one central atom with two outer atoms. Now we can switch to one central atom with three outer atoms. And I will keep this one for next lecture. Thank you, guys. Okay, before end the presentation, please be patient when it comes to the lab, practice classes, and SI. Okay. We are working with the Losses Center, ITLE, and head of the Department of Chemistry, the College of Art and Science. Frankly, it's not really easy for the university to come with many facilities to kind of make any faculty on this campus happy, or I don't know, book room or study rooms for them so that they can record their videos, or assign some people to help them with the editing and other stuff. So please be patient about it. We will do our best to do our job, teach you what we're supposed to do, and save your grade, because it's your right. Thank you, guys.